Listening practice, an expanded and refined version of Part 1, Fundamentals of Construction Technology, with additional subsections and deeper insights for a more comprehensive chapter structure. Part 1, Fundamentals of Construction Technology Chapter 1, Introduction to Construction Technology 1. Historical evolution of construction methods, prehistoric and ancient techniques, mud, stone, timber, Roman and Gothic engineering innovations, Industrial Revolution, steel, concrete, and mechanization, digital age, from CAD to AI-driven construction to the role of technology in modern construction, enhancing efficiency, speed, and precision, reducing costs and waste through automation, improving safety and risk management. 3. Key challenges in construction technology, high initial costs and ROI considerations, skilled labor shortages and training needs, regulatory and compliance barriers, sustainability versus profitability trade-offs. 4. Future trends shaping the industry, AI and generative design for optimal structures, circular economy and zero-waste construction, biofabrication, e.g., mycelium-based materials, space and underwater construction prospects. Chapter 2, Construction Materials from Traditional to Advanced, subsections to be expanded in your request. Chapter 3, Construction Techniques and Methodologies, subsections to be expanded in your request. Key enhancements in this version. 1. Deeper historical context traces technological shifts from ancient methods to futuristic trends. 2. Balanced perspective discusses not just benefits but also challenges, costs, regulations, labor gaps. 3. Future-focused highlights cutting-edge trends like biofabrication and extraterrestrial construction. Would you like similar expansions for chapters 2 and 3, or focus on another part of the book? Chapter 2, Materials in Construction. 1. Traditional construction materials, concrete, composition, cement, aggregates, water and admixtures, types, ready-mix, precast, high performance, lightweight, strengths and limitations, durability versus carbon footprint, steel, structural properties, tensile strength, flexibility, applications, beams, columns, reinforcements, corrosion protection, galvanization, coatings, wood/timber, engineered wood, CLT, GLILOM, LVL, versus solid lumber, sustainability and carbon sequestration. Benefits, fire resistance and treatment methods, masonry, brick, stone, block, load-bearing versus veneer applications, mortar types and modern masonry techniques, thermal mass and energy efficiency. 2. Advanced and innovative materials, fiber-reinforced polymers, FRP, types, carbon fiber, glass fiber, aramid, uses, structural strengthening, lightweight bridges, self-healing concrete, microcapsule and bacterial healing mechanisms, applications in high durability infrastructure, smart materials, shape memory alloys, seismic resistance, thermochromic and photovoltaic integrated materials, transparent materials, transparent aluminum, ALAN, and glass composites, applications in modern architecture. 3. Sustainable and eco-friendly materials, recycled and upcycled materials, recycled plastic bricks and composite lumber, reclaimed wood and demolition waste reuse, low-carbon alternatives, hempcrete, bamboo, and mycelium-based composites, geopolymer concrete, fly ash-based, energy-efficient materials, aerogels for insulation, phase change materials, PCMs, for thermal regulation, biodegradable and circular economy materials, bio-based binders and non-toxic paints, cradle to cradle. Certification in material selection. Key discussion points for the chapter, comparative analysis, cost versus performance of traditional versus advanced materials, case studies, iconic buildings using innovative materials, e.g., The Edge, Bosco Verticale, future directions, lab-grown materials and AI-optimized composites. Would you like to add testing standards, ASTM, ISO, or a section on material selection criteria? Chapter 3, Construction Techniques and Methods 1. Conventional construction techniques, on-site, stake-built, construction, process, sequential phases, excavation, foundation, framing, finishing, pros, design flexibility, customization, cons, longer timelines, weather dependency, higher waste, heavy civil construction methods, cast-in-place concrete for bridges/dams, steel erection techniques for high-rises-2. Prefabrication and off-site construction, prefabricated components, precast concrete, walls, beams, columns, volumetric modules, bathroom pods, kitchen units, panelized construction, wall, floor, and roof panels, open/closed systems, speed of assembly versus transportation limits, modular construction, full room/unit fabrication in factories, case studies, high-rise housing, hospitals, schools, advantages, quality control, reduced waste, 30–50% faster builds-3. 3D printing in construction, technologies and materials, extrusion-based, concrete, clay, polymers, powder bonding, D-shape for complex geometries, applications, affordable housing, icons 3D printed homes, bridges, MX3DS steel bridge in Amsterdam, military and disaster relief structures, challenges, regulatory approval and structural codes, scalability and printer size limitations-4. Hybrid and emerging methods, tilt-up construction, on-site casting and lifting of concrete panels, insulated concrete forms, ICFs, energy-efficient, monolithic wall systems, robotic assembly, bricklaying robots, Hadrian X, autonomous welding/demolition machines-comparative analysis method speed cost efficiency sustainability best for conventional construction slow moderate low, high waste, custom, high-end projects modular construction very fast high medium, less waste, repetitive housing/commercial 3D printing fast, small scale, low, material savings, high, minimal waste, prototypes, affordable housing-future trends, 4D printing, self-assembling structures, AI-optimized construction sequencing, biohybrid materials, living walls, algae-based structures. Would you like to include case studies of landmark projects, e.g., Singapore's prefabricated skyscrapers, Dubai's 3D printed office, or safety considerations for each method? Chapter 4, Building Information Modeling, BIM, 1. Fundamentals of BIM, Definition and Core Principles, Digital Representation of Physical/Functional Characteristics, 3D, 4D, Time, 5D, Cost, 6D, Sustainability, and 7D, Facility Management, Dimensions, Open Standards, IFC, COBie, and Interoperability, BIM Software Ecosystem, Design and Modeling, Revit, ArchiCAD, Rhino and Grasshopper, Coordination, Navisworks, Solibri, Analysis, Autodesk Insight, Energy Plus, for Performance, -2. Applications across the project lifecycle, design phase, parametric design and generative AI integration, clash detection, MEP versus structural conflicts, daylight, wind, and energy simulations, planning and pre-construction, 4D scheduling, synchro, Primavera integration, quantity takeoffs and cost estimation, 5D BIM, virtual reality, VR, walkthroughs for stakeholder reviews, construction execution, on-site BIM via tablet/AR, HoloLens, Trimble XR, progress tracking with laser scanning/photogrammetry, RFID/NFC for material tracking, operations and maintenance, 6D/7D BIM, digital twin integration for facility management, predictive maintenance using IoT sensor data-3. Global Case Studies Project BIM Innovation Outcome Shanghai Tower Wind Load Optimization via Parametric BIM 14% steel savings, $58 million cost reduction, Crossrail, UK, federated BIM for 40 plus contractors 10,000 plus clashes resolved pre-construction Singapore's BIM mandate nationwide 5D BIM for public projects 25% faster approvals, 15% cost savings. 4. Challenges and future trends, barriers to adoption, high software/training costs, legal risks, data ownership, liability, resistance to cultural change in traditional firms, next-gen BIM, AI-driven BIM, automated code compliance checking, blockchain for BIM, secure version control and contracts, BIM and GIS integration, smart city planning. Key takeaways, BIM reduces rework by up to 40%, McGraw-Hill, mandates, UK, Level 2, EU, UAE, and India now require BIM for large projects. Emerging markets face skills gaps but benefit from cloud-based solutions. Would you like to explore BIM for infrastructure, roads, bridges, or comparisons with CAD in more depth? Chapter 5, Automation and Robotics in Construction. 1. Robotic on-site construction. A robotic bricklaying and masonry, technologies, Hadrian X, FBR, robotic arm with dynamic stabilization, 200 plus, SAM100 semi-automated mortar application and bricklaying, advantages, 5x faster than manual labor, 99% precision, reduced musculoskeletal injuries, limitations, high initial cost, $2M and for Hadrian X, limited to standardized brick designs. Brick/hour, B. Robotic welding and steel assembly, systems, welding drones, e.g., flyability. ILAOS for confined spaces, exoskeletons, exovest for worker endurance, case study, MX3DS 3D printed steel bridge, Amsterdam, robotic arms used for complex joints. 2. Drones, UAVs, in construction. A. Surveying and mapping, LiDAR versus photogrammetry, LiDAR, high accuracy terrain models, e.g., mining, highways, photogrammetry, orthomosaic maps for progress tracking, PIX4D, drone deploy, regulations, FAA Part 107, US, EASA, EU, certification. B. Inspection and monitoring, applications, roof inspections, thermal imaging for leaks, tower crane safety checks, AI integration, Skycatch AI-powered defect detection from drone imagery. 3. Autonomous heavy equipment. A. Self-driving machinery, bulldozers and excavators, Caterpillar D6X AI-guided grading, 0.5-inch accuracy, Build Robotics autonomous trenching for utilities, benefits, 24/7 operation in hazardous zones, mining, nuclear sites, B. Autonomous trucks and haulers, Komatsu's AHS, autonomous haulage system, 300 plus driverless trucks in global mines, Volvo TA15 electric, self-driving dump trucks for quarries. 4. Emerging trends and challenges. A. Human-robot collaboration, cobots, collaborative robots, Boston Dynamics Spot for site inspections, Dusty Robotics autonomous layout printing. B. Barriers to adoption, cost, small firms struggle with ROI, $500K and for robotic systems, regulation, lack of standards for autonomous site vehicles, workforce resistance, fear of job displacement. See future outlook, swarm robotics, multiple drones/robots coordinating tasks, AI and vision systems, real-time. Obstacle avoidance, NVIDIA Isaac, case study, Zurich's DFAB house, robotic fabrication, 3D printed ceilings and robot assembled rebar, result, 60% faster construction, near zero waste. Comparative table, automation technologies. Technology key players best for productivity gain. Robotic bricklaying FBR, Hadrian X, housing, repetitive structures 5x speed. Autonomous excavators. Build Robotics, CAT Earthworks, utilities 30% fuel savings. Inspection drones. DJI, flyability bridges, rooftops 80% time reduction. Would you like to explore specific regulatory frameworks, OSHA, ISO, or dive deeper into AI-driven predictive maintenance for robots? Chapter 6, Green and Sustainable Construction 1. Energy Efficient Building Design. A passive design strategies, orientation and daylighting, optimal window placement, e.g., south facing in northern hemisphere, thermal mass, materials like rammed earth or concrete for temperature regulation, natural ventilation, stack effect and cross ventilation designs. B. Active systems, HVAC innovations, variable refrigerant flow, VRF, systems, geothermal heat pumps, 50–70% energy savings, smart lighting, LED and IoT sensors, occupancy/daylight harvesting, C. Renewable energy integration, building integrated photovoltaics, BIPV solar windows, e.g., ubiquitous energy, wind turbines, small-scale vertical axis turbines for urban areas. 2. Green building certifications. A leadership in energy and environmental design, rating systems, LEED v4.1, platinum, gold, silver, certified, categories, energy, 33%, materials, 15%, water, 10%, case study, The Edge, Amsterdam. LEED platinum, 102% energy surplus. B. BREEAM, Building Research Establishment Environmental Assessment Method, UK versus global standards, BREEAM outstanding, greater than or equal to 85%, versus LEED platinum, innovative credits, pollution reduction, ecological impact. C. Other systems, WELL building standard, focus on human health, air, water, light, living building challenge, LBC net zero energy/water/waste. 3. Net zero and passive house standards. A net zero energy buildings, NZEB, key components, airtight envelope, less than or equal to 0.6 ACH at 50 Pa, on-site renewables, solar/wind and battery storage. Global examples, Bullet Center, Seattle 250% energy surplus, Powerhouse Bratterkaya, Norway -22 kWh/m superscript 2/year. B. Passive house, passive AOS, principles, super insulation, R40 plus walls, heat recovery ventilation, greater than or equal to 75% efficiency, cost versus savings, 5–10% upfront premium, 90% energy reduction. 4. Sustainable materials and circular economy. A low-carbon materials, cross-laminated timber, CLT carbon-negative alternative to steel/concrete, hempcrete, carbon sequestering insulation. B. Waste reduction strategies, design for deconstruction, DFD modular, reversible connections, C&D waste recycling, 75% diversion mandates, e.g., EU Circular Economy Package. 5. Challenges and future trends. A. Barriers to adoption, higher costs, 2–15% premium for green buildings, recouped in 5–10 years, skills gap, lack of trained passive house/LEED professionals. B. Innovations on the horizon, carbon capture concrete, CO2 mineralization, e.g., carbon cure, algae facades, bioreactive panels for air purification. Case study, Bosco Verticale, Milan, design, 900 trees, 20,000 plants on Twin Towers, impact, 30% biodiversity increase, 15 degrees Celsius summer cooling. Comparative table, Green Certification System Focus Area Key Metric Notable Project LEED Holistic Sustainability Energy/Water Efficiency. The Edge, Amsterdam, BREEAM Ecological Impact Life Cycle CO2 Assessment 1 Angel Square, UK, Passive AOS Energy Efficiency less than or equal to 15 kWh/m superscript 2/year Heating. Cornell Tech, NYC, would you like to explore policy drivers, e.g., EU Green Deal, Inflation Reduction Act incentives, or dive deeper into regenerative design principles? Chapter 7, Smart Construction and IoT Integration. 1. IoT Sensors for Structural Health Monitoring, SHM, a real-time monitoring systems, vibration and load sensors, detect stress in bridges, high-rises, e.g., hollow builder and strain gauges, corrosion sensors, embedded in rebar to alert for concrete degradation, tilt meters, monitor foundation shifts in real time. B. Wireless sensor networks, WSNs, LP1 technologies, LoRaWAN, NB-IoT for long-range, low-power data transmission, edge computing, on-site data processing to reduce cloud dependency. See case study, Golden Gate Bridge, 2,100 plus sensors track wind, corrosion, and traffic loads too. Smart buildings and home automation. A. Core systems, energy management, smart HVAC, AI-optimized climate control, e.g., Siemens Desigo, dynamic glass, electrochromic windows, view glass, adjust tint based on sunlight, occupancy optimization, people counting sensors, density control via infogrid. B. Predictive maintenance, fault detection, AI analyzes HVAC/electrical data to preempt failures, plumbing IoT, PHY and smart water valves detect leaks, 1 SEC response, C. Human-centric. Automation, voice/app control, integration with Google Home, Apple HomeKit, wellness tech, CO2/VOC monitoring, Aware, AirThings, -3. AI and machine learning in construction management. AI-driven project optimization, schedule forecasting, Alice Technologies, generates 10,000 plus schedule scenarios in minutes, cost prediction, Doxel AI, LiDAR and AI tracks progress versus budget in real time. B. Risk mitigation, computer vision, open space, 360 degrees photo documentation with defect detection, safety compliance, helmet/vest detection via Everguard. C. Generative AI, design automation, test fit for instant site feasibility studies. Permitting, Upcode's AI scans 1M and regulations for compliance. -4. Integration challenges and solutions. Challenge solution data silos, unified platforms, Autodesk Tandem, cybersecurity risks, blockchain secured IoT, ZIC security, high initial cost SaaS models, Sensora systems, -5. Future trends, digital twins, live sync between physical buildings and IoT data, City Zenith, 5G plus IoT, ultra-low latency for autonomous equipment control, AI foreman, autonomous drones and robots guided by NVIDIA. Metropolis case study, the Las Vegas Message Sphere, IoT deployment, 580,000 square feet of programmable LED exterior plus 164,000 speakers, AI integration, real-time crowd flow optimization. Comparative table, smart construction tech technology vendor examples. ROI IoT SHM Sensi, Pillar Technologies 20% maintenance cost reduction. AI scheduling Alice, N-Plan 15% fewer delays. Smart Glass View, Sage Glass 30% energy savings. Would you like to explore ethical concerns, data privacy, job displacement, or dive deeper into AI augmented design tools like Hypar or Swap? Chapter 8, Advanced Structural Systems. 1. High-rise construction technologies. A. Core innovations, megacolumns and outrigger systems, Burj Khalifa, 828M buttressed core and high-strength concrete, SCC, Shanghai Tower, 632M twisted facade reduces wind loads by 24%, modular steel composite hybrids, Singapore's Clement Canopy, prefabricated modules stacked to 40 stories, material advances, UHPC, ultra-high performance concrete 200 plus MPa strength, grade 120 steel, lighter, stronger frames. B. Construction techniques, jump form systems, self-climbing formwork, e.g., Doka SKE 100, top-down construction, simultaneous basement/exoskeleton work. 2. Seismic resistant design. A. Energy dissipation systems, base isolation, lead rubber bearings, e.g., San Francisco Airport, friction pendulum bearings, 3M displacement capacity, dampers, tuned mass dampers, Taipei 101S 660-ton steel sphere, viscous fluid dampers, Japan's KYB systems. B. Ductile design principles, capacity design, ensure plastic hinges form in beams, not columns, buckling restrained braces, BRBs yielding core absorbs quake energy CAI and simulation, finite element analysis, via ANSYM models for nonlinear seismic behavior, case study, Torre Mayor, Mexico City survived 7.6 quake with damp moment frames. 3. Lightweight and tensile structures. A tensile membrane systems, materials, PTFE coated fiberglass, ATFE foil, e.g., the Eden Project, cable nets, Munich Olympic Stadium, 75,000 square meters acrylic glass canopy B space frame and grid shells, 3D printed nodes, MX3DS metal grids for complex geometries, wooden grid shells, center poppy dumets, 77M freeform roof, C air supported structures, inflatables, Tokyo Olympic Stadium's temporary domes, military/disaster use, rapid deploy shelters, HDT. Global, -4. Comparative analysis system best for material efficiency notable project diagram rids iconic skyscrapers 20% steel reduction Gherkin, London, base isolation earthquake zones 50% plus force reduction Apple Park, California, ATFE cushions lightweight roofs 1% weight of glass water cube, Beijing, -5. Future frontiers, 4D printed structures, self-morphing components, MIT's active origami, bioconcrete, calcite precipitating bacteria for crack repair, space construction, NASA's lunar habitats with 3D printed regolith. Case study, Morpheus Hotel, Macau, exoskeleton, freeform steel grid saves 30% materials versus conventional frame, algorithmic design, Zaha Hadid architects and parametric engineering. Would you like to explore kinetic structures, moving facades, or dive deeper into nanomaterials like graphene reinforced composites? Chapter 9, Geotechnical Engineering and Foundation Technologies 1. Soil Stabilization Techniques. A mechanical stabilization, vibrocompaction, densifies loose sands, e.g., stone columns for liquefaction mitigation, dynamic replacement, heavy tamping to replace weak soil with granular fill. B. Chemical stabilization, lime/cement treatment, reduces clay plasticity, 5-10% lime mix, jet grouting, high pressure injection for soilcrete columns, 1-3 m diameter, polymer stabilizers, eco-friendly alternatives, e.g., terrazole, C. Biological stabilization. Microbial-induced calcite precipitation, MICP bacteria, Sporosarsina pasteuri, bind soil particles, root reinforcement, vegetation for slope stability, e.g., Hong Kong's hillsides. -2. Deep foundation systems. A pile foundations, types, driven piles, steel/H concrete immediate load capacity, board piles, cast in situ for high loads, 2-3 m diameters, screw piles, helical plates for low vibration installations. Innovations, Osterberg cell testing, measures pile capacity in situ, FRP piles, corrosion resistant for marine environments. B. caissons, floating caissons, sunk into place for bridges, e.g., San Francisco-Oakland Bay Bridge, pneumatic caissons. Pressurized air for underwater work, historical use in Brooklyn Bridge, C. retaining systems, secant/tangent pile walls, interlocking piles for deep excavations, diaphragm walls, 1.5 m thick reinforced concrete for urban basements. -3. Ground improvement methods. A. vertical drains, prefabricated vertical drains, PVDs accelerate consolidation, e.g., wick drains. B. soil nailing and anchoring, soil nails, grouted tendons stabilize slopes, e.g., Hong Kong's highway cuts, ground anchors, pre-stressed cables for retaining walls, up to 2,000 knots capacity. See advanced techniques, vacuum consolidation, speeds up settlement in soft clays, e.g., Changi Airport expansion, electroosmosis, electric currents drain water from silts. -4. Case studies. Project challenge solution outcome Burj Khalifa weak carbonate soil 450,000 plus tons Kansai Airport, Japan, liquefiable seabed earthquake-resistant runway Millau Viaduct, France, karstic limestone bridge piers globally 194 board piles, 47 m depth, supports sand compaction piles rock anchors and micropiles tallest -5. Future trends, AI-powered geotech, machine learning predicts soil behavior from CPT data, self-healing foundations, microcapsules repair cracks autonomously, nanotechnology, graphene-enhanced grouts for ultra-strength stabilization - comparative table, foundation systems method load capacity best soil type cost, per unit, driven piles 503,000 kn dense sand, stiff clay $80 $150 linear footboard piles 5,000 kn variable, rock/clay, $200 $500 linear footstone columns 100-300 kPa soft clay, loose sand $15 30 m superscript 2 would you like to explore offshore geotechnics, wind turbine foundations, or disaster-resistant retrofitting techniques? Chapter 10, Digital Project Management Tools 1. Construction Scheduling Software A Primavera P6, Oracle, Key Features, Critical Path Method, CPM, with multi-project dashboards, resource leveling for labor/materials optimization, use case, Crossrail, London managed 10,000 plus activities with 200 plus subcontractors. B Microsoft Project, Pros, Gantt chart simplicity and Office 365 integration, cost tracking with earned value management, EVM, limitations, weak in multi-user collaboration versus Primavera C. New Gen alternatives, Procore Scheduler, drag and drop interface with BIM Sync, Asta Power Project, 4D scheduling with risk simulation - 2. Cloud-based collaboration platforms A Autodesk Construction Cloud, modules, BIM 360, design coordination, PlanGrid, paperless markups, case study, LA Stadium, 4,000 plus users access 60,000 plus files in real time. B Trimble Connect, IoT integration, equipment telemetry and schedule updates, global projects, supports offline sync for remote sites. C OpenSpace and HoloBuilder, 360 degrees documentation, AI-powered progress tracking via site photos - 3. Real-time progress tracking A laser scanning and drones, LiDAR versus photogrammetry, LiDAR, plus or minus 2 mm accuracy for MEP clash detection, DJI Phantom 4 RTK, 1 cm GPS precision for earthworks. B RFID/NFC tracking, materials management, Triax Spot R, tags on rebar/pipes trigger location alerts, labor productivity, unearth, GIS maps show crew movements versus schedule. C AI-driven analytics, Doxel AI, compares laser scans to BIM 4% completion, BillDots, hard hat cams auto-detect delays, e.g. missing drywall, - 4. Integration challenges and solutions challenge tool/strategy - data silos Autodesk Tandem, Unified CDE, change order delays. Brick, AI cost forecasting, time cost trade-off. Synchro 4D, scenario modeling, - 5. Future trends, digital twins, live sync between schedules and IoT sensors, Sensorot, blockchain, smart contracts auto pay upon milestone completion, Bridget, AR overlays, Microsoft HoloLens shows schedule delays on-site - case study, The Big Dig, Boston, TechUsed, Primavera and RFID for 12,000 components, result, 15% fewer delays despite 7,000 change orders - comparative table, top tool software best for AI feature cost - Primavera P6 megaprojects risk analysis $2,500/user/year Procore midsize GCS auto daily reports $800/user/year Doxel AI subcontractor tracking LiDAR versus BIM delta detection custom pricing - would you like to explore lean construction tech, last planner system apps, or cybersecurity for cloud platforms. Chapter 11, Construction Safety and Wearable Tech 1. PPE Innovations. Exoskeletons, Types and Functions, Passive Suits, e.g., exo-vest reduces 40% shoulder strain for overhead work. Active exos, e.g., Sarco's Guardian XO20X strength amplification for lifting. ROI, 25% fewer musculoskeletal injuries. OSHA estimates $1 million saved per incident avoided. B. Smart helmets. Features: DACRI Smart Helmet, AR overlays for hazard alerts and thermal vision. JLG ClearSky, noise cancellation and real-time translation for multilingual crews. Case study: Bechtel's IoT helmets cut fall incidents by 60% on LNG projects. See sensor embedded gear. Smart gloves, vibrate when near pinch points. Strong arm tech, safety vests, GPS and vitals monitoring. Site-aware. -2. Hazard detection systems. AI-powered cameras, proximity alerts. Everguard, AI detects workers near heavy equipment, 90% accuracy. Fire/gas risks. Notion sensors, wireless multi-hazard detection. B. Wearable environmental monitors. Black-Klein safety, tracks VOC, O, and HS levels with SOS alerts. Work alert, heat stress warnings via wristbands. See autonomous drones. Flyability. Ilias 3, confined space inspections, no GPS needed. SkyX, automated patrols for unauthorized site access. 3. VR/AR for safety training. A. Virtual reality simulations, hazard drills. Boyd Cat, VR electrocution/fire scenarios. PIXOVR, multiplayer fall protection training. Efficacy: 80% better retention versus classroom training. University of Maryland study. B. Augmented reality on-site, HoloLens 2, overlays OSHA codes onto equipment. Trimble XR10, XYZ reality, AR error proofing for MEP installations, plus or minus 3 mm accuracy. See metaverse applications, safety audits, digital twin simulate collapse scenarios. Safe site, remote expert guidance, live AR annotations from off-site engineers. 4. Challenges and adoption barriers. Issue solution high costs. Leasing models, e.g., Sarco's Flex, data privacy. Blockchain secured wearables, ZIG, worker resistance. Gamified training, BIM and VR rewards. 5. Future trends, autonomous safety drones, AI patrols for real-time hazard mapping, biometric hard hats, EEG sensors detect fatigue/distraction, self-healing materials, nano-coated PPE repairs. Minor tiers. Case study, Shell's Prelude FLNG, tech used, exoskeletons and AR helmets for confined space welding. Result: 0 lost time injuries over 50 work hours. Comparative table, safety tech ROI technology injury reduction cost per unit. Key vendor exo-vest 40% shoulder injuries $5,000 exo-bionics Everguard AI 50% struck by incidents $15K/site/year Everguard AI PIXOVR training 80% faster compliance $400/headset PIXOVR Would you like to explore OSHA/NIOSH regulatory tech compliance or psychosocial safety, AI mood detection? Chapter 13, Global Case Studies in Construction Innovation 1. Iconic Smart Cities. ANEOM, Saudi Arabia, The Line, Zero Carbon, AI governed city stretching 170 kilometers with no cars, modular robotics, 3D printed foundations and autonomous logistics. Energy, 100% renewable, wind/solar/hydrogen. Challenges, $500 billion budget. Geopolitical risks. B. Singapore's smart nation, digital twin, virtual replica of entire city for traffic/utility management. Prefab revolution, PPVC, prefabricated pre-finished volumetric construction 40% faster high-rise builds. Robotized concrete printing for public housing. C. Masdar City, UAE, Net Zero Urban Lab, wind towers and PV canopies reduce energy use by 40%. autonomous pods, no fossil fuel vehicles allowed. 2. Disaster resilient structures. A earthquake resistant innovations, Taipei 101, Taiwan, 730-ton tuned mass damper survives typhoon/quakes, Istanbul seismic retrofit, base isolated hospitals, 1,500 plus buildings upgraded, B flood adaptive architecture, the float house, New Orleans amphibious foundation rises with water, Netherlands Meislandkering, AI controlled storm surge barrier. C wildfire resistant communities, California's fire resilient homes, non-combustible materials. Fiber cement, metal roofs, defensible space drones for early detection. 3. Affordable housing solutions. A 3D printed communities, Icons Villages, Mexico/Texas, $4,000 homes printed in 24 hours, Vulcan 2 printer, layered concrete with thermal insulation. B modular microhousing, Singapore's HDB flats, prefab bathroom units slashes costs by 20%, Cargotecture, USA shipping container homes, $50K $150K, C policy-driven models, Vienna's social housing, 60% of residents in city-subsidized units, India's PMAY, 30M and homes via geopolymer concrete and blockchain payments. 4. Lessons learned project innovation scalability. The line, NEOM, AI urban planning limited to oil-rich economies. Icons 3D homes rapid, low-cost builds zoning law barriers. Singapore PPVC high-rise modular efficiency high initial factory costs. 5. Future outlook, climate adaptive cities, floating neighborhoods, Oceanics Busan, AI-powered slum upgrades, Mumbai's Dharavi redevelopment, space habitat prototypes, NASA's Mars ice home concepts. Comparative table, Smart City Metrics City Key Tech Sustainability Claim Criticism NEOMAI, 3D Printing, Hydrogen Zero Carbon Human Rights Concerns. Singapore Digital Twin, Robots 80% green buildings by 2030 high density equals privacy loss. Masdar Solar, autonomous transport first net zero city limited cultural vibrancy. Would you like to explore failed smart city projects, e.g., Songdo's lessons, or community-led urban innovations like Medellin's escalators? Chapter 14, The Future of Construction Technology. 1. AI-driven construction sites. Autonomous construction fleets, self-optimizing sites, AI coordinates robots, drones, and human crews in real time, e.g., Doxel's autonomous progress tracking, predictive analytics. Alice Technologies, simulates millions of schedule scenarios to prevent delays. Build Robotics, AI-guided excavators with centimeter precision. B generative design and AI architects, Autodesk's Dreamcatcher, AI generates 10,000 plus design options meeting cost/safety specs. NVIDIA's Omniverse, digital twins simulate weather/stress impacts before breaking ground. C quality control via computer vision, OpenSpace AI, compares 360-degree side photos to BIM models, flagging defects. Sensora Systems, autonomous cameras detect missing PPE or unsafe behavior. 2. Bio-inspired architectural designs. A biomimicry in structures, termite mound ventilation, Eastgate Center, Zimbabwe, uses 90% less energy. Spider silk concrete, researchers add silk proteins for crack resistance. B living materials, mycelium bricks, grown in 5 days, compostable, e.g., the Hi-Fi Tower, algae facades, bioreactive panels absorb CO2. BIQ House, Hamburg, C4D printed shape-shifting structures, MIT self-assembling furniture, programmable materials fold when heated, tunable. Stiffness bridges, adjusts load capacity via fluidic actuators. 3. Policy and regulatory impacts. A global standards for tech adoption, EU's Construction 4.0, mandates digital twins for public projects by 2030, Dubai's 3D printing law, 25% of new buildings must be printed by 2030. B labor and ethics challenges, reskilling programs, Singapore's built environment ITM trains workers in robotics, AI bias mitigation, ensuring algorithms don't favor cost over safety. C. Carbon penalties and incentives, concrete taxes, Norway's $50/ton CO fee on cement. Green subsidies, U.S. Inflation Reduction Act's $5 billion for low-carbon materials. Appendices 1. Glossary of construction technology terms, digital twin, virtual replica of a physical asset with live IoT data, circular economy, reusing materials to eliminate waste, e.g., cradle-to-cradle certification, passive AAS, ultra-efficient building standard, less than or equal to 15 kWh/m superscript 2/year heating, 2. Further reading and resources, books, The Fourth Industrial Revolution, Klaus Schwab, AI/Robotics Impacts, Biomimicry in Architecture, Michael Pollan, Reports, McKinsey's The Next Normal in Construction, 2025 Tech Forecasts, World Green Building Council's Net Zero Roadmap 3. Index, detailed keyword index spanning materials, technologies, and case studies from all chapters, future timeline, 2025-2050 year prediction likelihood 2025 50% of new U.S. homes use AI design tools high 2030 first major bioconcrete skyscraper medium 2040 moon base construction begins low would you like to add a section on space construction tech, NASA's lunar regolith 3D printers, or blockchain for supply chains?